Okay, so here's the first question. So suppose that the set of alternatives is some set Z. Okay? So Z, for simplicity, it doesn't have to be finite, but $1, $2, all the way up to $100. Basically, it's a finite set of monetary prices where all prices are multiples of $1. Okay? Again, it could be an infinite set actually, it doesn't really matter as long as it's a set of monetary prices. So preferences of JJ over lotteries LZ are defined as follows. When given any two lotteries, P and Q, all right, JJ considers the highest likelihood of getting a prize, regardless of how big or small this prize is. All right, so the highest likelihood of getting some prize. And concludes that lottery P is preferred to lottery Q if and only if the highest probability attached to a prize in P is higher than the highest probability attached to a prize in Q. All right? So more formally, JJ prefers P over Q if and only if maximum of PZ, well, here we're maximizing over prizes, over the probabilities of prizes. So therefore, Z is coming from this set Z. So max of PZ is greater than or equal to max of QZ. Okay? The question asks us to consider three lotteries, P, Q, and R. So P is defined as follows. You're going to get $100 with probability 0.5. All right, so the 0.5, the numbers inside the parentheses are the probabilities of that prize. So $100 with half probability and $90 with the remaining probability. So there are two possible prizes. Don't forget, this is kind of a shorthand version of writing a lottery. This lottery actually tells us more than that, indirectly. It says, for example, if you choose this lottery, there's no way you can win or earn, say, $89 or $10. These are all zero probability prizes. But we just ignore the zero probability prizes. Okay? So be careful about that. Q, however, has the following structure. $30 with probability 0.5, and then $20 with probability 0.3, and finally, one more prize, $10 with probability 0.2. Okay? And finally, R is equal to this lottery, $10 with probability 0.7 and $4. Okay, $4 with probability 0.3. Okay? So, part A was asking, how does JJ rank these three lotteries? Which one he prefers the most, which one he prefers the least, and so on. All right? And part B is JJ risk-averse, risk-loving, or risk-neutral. Give an example to support your claim and discuss how you would prove this claim. All right, so the question is asking three things. Determine whether he is risk-averse, risk-loving, or neutral, either one of those, right? You can't be, depending on how weird the preference relation is. Usually it's either risk-averse or neutral or loving. So we're going to determine this by inspection and then give an example to support our claim. And then we can talk about how we prove this claim in general. Part C, calculate JJ's certainty equivalence for lottery P. Okay. For this question, we basically need to remember, a few definitions, like what we mean by risk aversion or risk levying or risk neutrality, and then what it means certainty equivalence. How do we define it? Okay. Well, I'm going to give them along the way anyhow. So first, how does he compare P and Q? So here, any two lotteries are compared. Basically, JJ is looking at the highest probability, all right? And if the highest probability in P is higher than the highest probability in Q, well, then P is better. This is how he thinks. So what do you think? P versus Q. Well, when I look at P, what is the highest likelihood of getting a price? 0.5, right? I mean, both are equal probabilities. So with 0.5 probability, you're going to get a price. Well, you may say with probability 1, you're going to get some price. But yeah, I mean, all of those are lotteries. With probability 1, you will certainly get a price. So that's not, I mean, this is not what we're looking for. We're looking for those numbers in the parentheses because they are the PZs. So it's 0.5. So whenever JJ looks at lottery P, he actually sees only 0.5. He doesn't see $100. He doesn't see $90. He just sees 0.5. When he looks at lottery Q, what he sees, the maximum likelihood, which is 0.5 again. Well, let's do for R as well. When he looks at R, the only thing he sees is basically 0.7. So he says with 0.7 probability, I'm going to win something. All right? Well, yeah, but it's $10. Here, for example, you're going to win $100. All right, so this is the way he compares things. It could be awkward for you, but fine, it's the definition we have. So then the rest is simple, isn't it? P is preferred to Q if and only if this maximum number is greater than the maximum number of Q. So P and Q are actually giving us exactly the same lottery. Same highest likelihood. So therefore, JJ is going to be indifferent between P and Q. Right? You either use this notation and just say P and Q are, JJ is indifferent between P and Q, as you wish. But that's the conclusion between P and Q. Well, what about P, Q, with R? So clearly, R is preferred to P, and R is preferred to Q as well. So R is basically his top lottery, the best lottery from his point of view, and then comes P and Q. P and Q are indifferent. He's indifferent between these two. That's it. Is that clear? Any question? Well, so the second part may be a bit more challenging. This part is basically just to sort of push you to understand what this preference relation looks like. So in part B, the question is JJ risk averse, risk neutral, or risk loving? Well, and if you remember, a preference relation is called risk averse. That means for any for any lottery in this set LZ, well, we must have the sure lottery or degenerate lottery, E of P, is at least as good as P. If this is the case, well, we call the preference relation, or JJ, if that preference relation belongs to JJ, we call JJ risk averse. Risk loving, basically you just reverse the sign, meaning P is at least as good as this degenerate lottery. And risk neutral basically means he's indifferent between these two lotteries. So these are lotteries. You can't compare a lottery with some real number. So this is a lottery. So for example, for this P, that's critical, obviously. What is the, let me write it here. What is the degenerate lottery, E of P. So what is E of P? E of P is the expected value, not utility, expected value of the lottery P. And remember, the definition was basically Z, the price, times P of Z. We sum over all prices in set capital Z. And so this is E of P. This is the piece of definition we have. So, if this is the lottery, P, what is the expected value of this lottery? 100 times 0.5, 50, plus 90 times 0.5, 45. So basically it's 95. So this is E of P. E of P. What does it mean a lottery, a degenerate lottery, E of P? How can I write it in this fashion? It's like the prize, parentheses, its probability. Prize, in parentheses, probability. So how does it going to look like? 95, in parentheses, 1. Anything else? In a bigger parenthesis. What do you want me to do? Oh, okay. Yeah, well, yeah, sure. Agree. So $95 with probability 1. I calculated this just because I need to have a sense of how he will compare E of P with the lottery, this lottery with the lottery P itself. Because that will determine whether he is, it's not going to prove it, but it's going to determine whether this guy is risk averse or risk loving or risk neutral. All right? So, how does this guy, JJ, compares lottery EP, degenerate, versus lottery P? Highest probability of winning a prize here is 1. The highest probability of winning a prize here is 0.5. So clearly 1 is higher than 0.5, so he should choose this degenerate lottery. So can I say this? E of P is at least as good as P? Yeah. Well then, therefore, if you remember the definitions of risk aversion, risk loving, risk neutrality, it basically falls down into this category, right? JJ prefers the sure lottery over the lottery itself. The sure lottery of the expected value over the lottery itself. And in fact, we can generalize this for any P, right? Here P is just one specific example. But I can generalize this for any lottery, Q, R as well. If you think about it for a minute, JJ is going to prefer, let me get rid of this. I don't need it anymore. The expected value of Q, whatever it is, the $23. So this degenerate lottery will be preferred to the lottery Q itself. Why? Well, because in a degenerate lottery, the highest likelihood of winning a prize is always 1. Always. And in Q, the highest likelihood of getting a prize, well, that depends on Q, but it's either 1 or less than 1. So therefore, for any lottery Q, the degenerate lottery of EQ is always at least as good as the lottery Q. So that's basically how you prove that JJ is risk averse. You just pick one example to figure out in which category he falls in. I eliminated these two by just working on this lottery P. And then I need to generalize this for any lottery P or Q, whatever notation you want to use. Is that clear, guys? So what is the certainty equivalence of lottery P? Well, what is certainty equivalence? Well, let's look at the definition. Certainty equivalence is a price, right? It's a number, a dollar. It has a dollar sign in it. If you create a degenerate lottery with this price, well, then the decision maker should be indifferent with the lottery itself. And this should hold, I'm sorry, not hold. I'm not defining any property on the preference relation, but this is the way we define the certainty equivalence. So what price, a sure price, I should give JJ so that JJ is indifferent between this sure lottery and P. Remember what was P? P is this lottery. He's going to win $100 with half probability, 50% of the time, $90 with the remaining probability. So, what price do you think is going to satisfy this? Is it $5, $10, $20? Okay. So, or 90. Okay, interesting reasoning. But which one exactly? You don't know. A person's comparative certainty equivalence can be more than one thing, you say. Okay, could be. Could be 100, it could be 90. Well, how do you verify the definition? Did you? Consider sure lottery with $100. Is JJ going to be indifferent between that sure lottery with P? Yes or no question? Well, he's going to prefer the sure lottery, right? Okay. What about, so therefore 100 cannot be certainty equivalence. Because certainty equivalence must satisfy this. This is the definition. Well, what about 90? So if we give a JJ the sure lottery, $90 with probability 1, right? This is exactly what CEP, where CEP is equal to 90. So this is the sure lottery. Is he going to be indifferent between this lottery, the sure lottery, and P? No. Again, why? Remember, he looks at the highest likelihood, which is 1 here. And highest likelihood in P is 0.5. So he's going to go for this, not P. So therefore, neither 100 nor 90 is the certainty equivalence for JJ. But what is it then?
P of Q is the certainty equivalence.
Okay, interesting. Well, because remember, we said JJ is going to be indifferent between Q and P, right? Well, then you're suggesting that the certainty equivalence of P must be equal to, therefore, the expected value of Q, which is 23. Okay, but did you verify this definition? Always, guys, I have a formal definition. I love you having intuition, okay? But always go with the definition, formal definition, and check your intuition, okay? So let's check. What would be this lottery, CEP in your case? It is this lottery, right? You're going to get $23 with probability 1. Do you think JJ is indifferent between this and P? No, because this sure lottery gives him probability 1, and the highest likelihood is still 0.5. 1 is higher than 0.5, so therefore he's going to prefer this over P. So he will not be indifferent. I am looking some number, 1, 2, 3, I don't know, pi, infinite, I don't know, some number where JJ is going to be indifferent when I put probability 1 here. Yes. 0.5? Price 0.5. Short answer, no. Long answer, just write the sure lottery of 0.5. Can you see it? I'm going to give $0.5, with probability 1, right? This is the sure lottery. Is JJ indifferent? No, because this lottery gives probability 1, always. Remember, degenerate lottery always gives probability 1. However, P always gives, the highest likelihood of P is 0.5. Sometimes some things may not exist, all right? For example, a maximum of some functions may not exist, right? Or the min of a function may not exist. So some things may not exist. So I'm sorry you're looking for the certainty equivalence for this preference relation. For lottery P specifically. But unfortunately, it doesn't exist. There is no prize you can offer this guy, all right? No prize you can offer this guy where he will be indifferent between that sure lottery and P. And the reason is, the sure lottery, whatever prize you give him, will always give probability 1, right? And remember, JJ only looks at the probabilities. He doesn't care about the prize. He focused so terribly on the likelihood of getting a prize. So here in the sure lottery, it's always 1. Here in P, it's always 0.5. So there's no prize which is going to satisfy this. Hence, for this lottery P, certainty equivalence doesn't exist. In fact, we can generalize this conclusion and say, for this preference relation, for almost, unless the lottery is a degenerate lottery, there is no certainty equivalence. If H is your lottery, like $100 with probability 1, well then certainty equivalence of H does exist, and it is $100, right? So if the lottery itself is degenerate lottery, well then certainty equivalence of that lottery exists. Otherwise, it doesn't exist. So that's a weird preference relation. Just happens to be risk averse. So here is the second preference relation. Coco's preferences, again over the same lotteries, L of Z, where Z is the multiples of dollars, starting from 1, 2, 3, all the way up to 100. And as you see, it really doesn't matter where the Z's are coming from. What matters is the preference relation. When given any two lotteries, P and Q, Coco considers the prize in each lottery that is most likely. Okay, now he cares about prizes as well. So once again, let me read. Coco considers the prize in each lottery that is most likely, breaking ties in favor of higher price, if there is any tie. Okay, and concludes that lottery P is preferred to lottery Q, or P is better than Q, if and only if the most likely prize in P is higher than the most likely prize in Q. How does Coco rank these three lotteries? Let's compare P and Q. Again, given the definition, formal or informal, given the definition of the preferences, you need to understand what sort of value Coco is going to attach to those lotteries. Well, this time, Coco looks at the lottery and the most likely prize. He considers only the most likely prize. So here, what is the most likely prize? Well, both 100 and 90 are equally likely. So there's no one single most likely prize. But the question says, in case there is tie, he's going to break the ties by favoring the higher price. So therefore, from this I understand that whenever Coco looks at lottery P, he's going to see $100 or just 100. You can, by the way, just assume this as the utility of this lottery. In fact, we are kind of attaching a utility values. This is how we generate utility functions, right? When he looks at Q, what is he going to see? $30, because this is the most likely price. And when he looks at, this is 0.7, terribly. What is he going to see? $10. So the comparison is then pretty straightforward, right? Coco prefers P over Q and prefers Q over R. That's it. Any question? Question is then, B, is he risk averse, risk loving, risk neutral? What do you think? Just to get an intuition, again, pick a lottery, any lottery, all right? I mean, we worked on P, but let's work on R this time, all right? There's no reason, I just randomly picked R. So what is remember the definition of risk aversion, risk neutrality, risk loving. We need to compare two lotteries. One, which is degenerate lottery, expected value of lottery R. And then the second lottery is the lottery itself. We need to compare these two. All right? So, well, we already know what R is. Let's create this sure lottery. Well, it's, with probability 1, going to give ER. What is ER? The expected value of lottery R? 10 times 0.77 plus 4 times 0.3, 1.2. So therefore it is $8.2. Well, you may say, well, look, it's not in the set LZ. Is this a problem? Well, yeah, apparently I selected not so perfectly rounded numbers. So don't worry about it, okay? Usually when we define risk aversion, risk loving, etc., we don't really assume Z being finite. We assume Z can be any real number, all right? Because it's sometimes easier to define objects over unrestricted domains, okay? So don't bother with the fact that this is 8.2, not multiples of 1. Fine. All it matters is this is the sure lottery, E of R. So how does he compare this and this? I mean the lottery R. Do you think he's indifferent? He prefers the lottery R? Well, why? Well, because the most likely prize is $10, and the most likely prize is $8.2, clearly less. So therefore, he will actually say E of R is worse than R itself. Or put differently, R is better than E of R, the sure lottery E of R. So this clearly violates the definition of risk aversion. All right? We found one lottery, R, where the lottery itself is better than the sure lottery. So this guy is definitely not risk averse. Definitely not risk neutral because he's not indifferent. He strongly prefers R. So if he is something, he must be risk loving. So let me clean this. So what is the conclusion here then? As a result of two examples we had, right? One of them was R, and the other one is S. We just switched the likelihoods. That's it. It's a simple trick. But what happens is that there are some lotteries, all right, let's call them R, where the sure lottery is worse than the lottery itself. So he goes for the risky thing. However, there are some lotteries, like S, he actually prefers the sure lottery. So he goes for the sure thing rather than the risky thing. Okay? So, well, this example turned out to be something better than I expected because it causes more confusion, I hope. So, this preference relation is therefore neither risk averse, nor risk loving, nor risk neutral. Well, then what about the Coco's certainty equivalence for lottery P? That's the final thing. So what is it? The lottery P is, again, this guy. So it has to be, C of P has to be such that when I create this sure lottery, it must be indifferent to P. That's the definition, remember. So I have to find a price value where cocoa will be indifferent to P. What do you think it is? 100? Yes. Why is that? Well, remember, when cocoa looks at P, he looks at the highest, most likely price and breaks the ties when in favor of higher price. So therefore, when he looks at this price lottery, he's going to see 100. Well, when he looks at this lottery, there's only one price, and this price is being 100. So both lotteries, P and the certainty equivalence sure lottery, are going to bring him 100. So therefore, he's indifferent. Hence, his certainty equivalence at P is equal to 100. Well, very quickly maybe, what is his certainty equivalence at Q? And what is his certainty equivalence at R? For Q? 30. Well, because 30 is the most likely outcome. Price, I'm sorry. And what about R? Well, R is this guy. Well, again, the most likely is 10, so therefore it must be 10. All right. So for this preference relation, it happens that the certainty equivalence apparently does exist, at least in those lotteries.